So we're going to go ahead now and start with the second part of our thermodynamic experience. In a previous unit, it was called thermochemistry, and we only focused on what thing? The whole unit. Delta H, heat of reaction. Good news is you already know how to do most of this. Bad news is you are accountable for anything in that last unit, because the way these problems are structured on the AP, they don't separate the two. They like come together. So we need to really quickly just kind of remind ourselves when we were finding delta H, what were the different ways we could do that? Big Mama, which is right here. So we could find delta H using Big Mama. What else? Flippy thing. What else? There are three more I can think of. Would you say calorimetry? Yes. In calorimetry, we can figure out Q, right? What was the relationship between Q and H with the use of the thermometer? Yeah, negative Q equals delta H. So you are still, again, responsible to know those. So you're probably going to have to pull out those other in-class problems and go through them before this next test. Two more. What? Yes, stoichiometry. If they give you the delta H of a reaction, you can find the delta H of the reaction when maybe 20 grams of the reactant are used or whatever. It is a stoichiometric relationship between the delta H and the coefficients in the balanced equation. And then the last one. Nope, not RATLink. We haven't done that yet this year. We're going to do it next, though. We're going to do it tomorrow or the day after. Don't know. No one remembers bond energy? How did we find it using bond energy? Bonds broken minus formed. Yeah, bonds broken minus bonds formed. So revisit these mentally, and also you're going to might want to, before some quizzes and stuff, look through them. It's going to be really similar to what we're doing now with delta S and delta G. So on the board, I have some delta S values that we're going to use today, as well as some H, S, and G values on this side, just to save us time from having to look things up throughout the unit. So I think pretty much everything we need is on the board. But the main thing I want to show you is delta H, S, and G values can be found on tables, and their units are going to differ. So this is kilojoules per mole. The delta H and the delta G have the same units. Delta S, which we're going to talk about today, has different units. So any equation we use where we're involving two of these things with entropy, we have to watch our units. That's the biggest student mistake. So really important to pay attention to units in this unit. That's a lot of units. Okay, so first law of thermodynamics here. This is review. Says that energy is constant, can't be created or destroyed. So in an equation form, does energy of the system plus energy of the surroundings equal to 0 make sense to you? If I have a system and it loses energy, what does the surroundings do? Gain that same amount, right? But the sign is opposite, because one's losing and one's gaining, so when you add them, you get 0. So that's just an equation way of stating the first law. We know Big Mama here. And you should know about exothermic being negative, endothermic being positive, right? That's easy. So let's move on and talk about entropy. The second law of thermodynamics is stated, the entropy of the universe will increase for any spontaneous process. Nature tends toward disorder. If you don't believe it, look at your room after you clean it. How long does that last? In like seconds. Yeah. You know, think about a deck of cards. If you were to order a deck of cards, that's only really one way to appropriately have them in the right order, right? But how many different ways can it be disordered? Like unlimited. So nature just tends toward disorder. Now, in terms of this spontaneous process, in order to determine if something is spontaneous or not, you need to know something about delta H and delta S of the system. You've got to take both into account. You cannot just look at delta S of the system, and by system I mean what we've been doing, flippy thing, Big Mama, all that stuff. When we do those calculations, that's of the system, okay? You can't just look at delta H of the system or delta S of the system to determine if the thing's going to happen, if it's spontaneous or not. So we have to do it one of two ways. The first way we can determine spontaneity is delta S of the universe. If the delta S of the universe is positive, it means the reaction is spontaneous. Now, the AP got rid of the word spontaneous. They felt that students were connecting spontaneity with rate. They thought I think it's spontaneous combustion that makes students think that. But spontaneity has nothing to do with time. Rusting is spontaneous. But is that a fast process? No. So instead of spontaneous, they're going to ask you questions, and they're going to say thermodynamically favored. That's how they're going to ask you questions. They're not going to say, is it spontaneous? They're going to say, is it thermodynamically favored? In an answer, you can say spontaneous, though. You're allowed to use that verbiage in a response. Just know you're not going to see that in a question. You're going to see thermodynamically favored. So, in order to find delta S of the universe, we need to find delta S of the system, and this is through all the ways we already know how to do. You can do Big Mama on delta S. You can do flippy thing, all the same things. We also then need to find delta S of the surroundings. This is a new thing that you're going to have to memorize. So again, this is just of the system. You find delta S the same standard way you already know. To find delta S of the surroundings, it is delta H of the surroundings divided by temperature. So if you look up here, you notice the units on delta S is joules per mole Kelvin. Temperature is a big component of disorder because as things heat up, molecules go crazy. So temperature is an important factor. So delta S of the surroundings is delta H of the surroundings divided by T. Well, anyone have an idea how I can find the heat of the surroundings? Doing stuff I already know how to do? Think back to the first law of thermo. Exactly. Negative delta H of the system. So we're going to find delta H the normal way, change the sign, and divide it by T, and that is delta S of the surroundings. So remember when I said spontaneity or thermodynamic favorability depends on H and S? Well, delta S of the system is S. Delta S of the surroundings is really dealing with H. So you've got to know both things before you can determine if a reaction is thermodynamically favored. So we're going to do one of these problems soon, in a minute. So this is just the kind of flow of the equation that we went through. Delta S of the universe is delta S of the system plus the surroundings. Delta S of the universe is equal to delta S of the system, which is really delta H of the surroundings over T. But that's really minus delta H of the system over T. So at the end of the day, this is how you're going to be calculating delta S of the universe. Both of which you can use all the traditional ways to find those values. Big Mama, flippy thing, all of that. Okay, let's jump into doing some problems. Whew, this first one's rough. I don't know if you can handle it. Calculate delta H for the following chemical reaction. What do we do with the data that we have in the table? What do we do? Big Mama, why are y'all so quiet? Is that like a revelation that you use Big Mama on this? Okay. Is it so easy you're not saying something, or is it so hard you're not saying something? Big Mama, we have our heats of formations. We're going to do products minus reactants. Delta H is equal to, looking at our products, 1 times aluminum chloride, negative 704 kilojoules per mole, minus, oh, look at the free energy of those elements, the delta H of those free elements. They're 0, right? The delta H of free elements are 0. Look up at the table. The delta G of free elements are 0. Look at the delta S. Not 0. So just remember that. Don't assume everything is 0 for free elements. It's not. All right, so what is our delta H? And you don't need a calculator for this. I'll hit you in the face if you try to pull out a calculator for this one. What is it? Minus 704 kilojoules per mole of reaction. So whenever we're reporting a delta H, delta G, or a delta S, we always want it on the AP per mole of reaction. That's why we have a per mole over there. Some people argue in some textbooks that this one is a mole, cancels out with that mole, but they're not talking about that mole. They're talking about 1 mole of this reaction, 1 mole of the whole reaction. That is the value. Okay, easy peasy. Moving on. Predict whether the entropy of the systems increase, remains constant, or decreases when the following processes occur. Explain your reasoning. So remember, entropy is disorder. As disorder increases, the universe likes that. It's positive. As disorder decreases, it is negative. So ice melting at 0 means, where is it? What's happening at 0? What is an equation that represents this? Let me put it that way. Ice melting. Thank you. Solid to liquid. Boy, y'all are giving me great hope for the AP exam right now. Very excited. So, entropy, is it increasing or decreasing? Increasing. So our predicted delta S sign is positive or negative? Positive. So they want us to prove this specific one with math, which is fine because I do have it on the board here. I've got the solid over there. The liquid, water liquid's delta S is 69.91. I'm doing Big Mama here. Products minus reactant of solid 37.99. And this is joules per mole K. Does that number come out to be positive? Yes, that's all they want us to do is prove that. Everyone understand? I just did Big Mama with those, product minus reactant, using stuff from the tables. Okay, for the rest, we're just going to kind of talk about the states of matter. A precipitate forms in an aqueous solution. What happened to disorder there? It decreased. Disorder decreases, so our sign of delta S is negative. A solid dissolves in water. Increases, so it is a positive delta S. And gas condenses to a liquid. Decreases, negative delta S. So states of matter is a common way for the AP to ask you about entropy. If you're not told, you might have to look at equations and figure it out by looking at the states they provide. So we're going to calculate this using the values from problem 1. We have our entropy values on that problem on the table. But I want to predict first. We're going from a solid and a liquid to just solid. What's happening to entropy? It's going down. So what sign do we predict on our delta S? Negative. So we're going to go ahead and calculate that and see if our prediction is true. So you guys can go back, look back easier than I can flip back. Whoops, we're doing delta S. Big Mama, 1 times, what's aluminum chloride's entropy? 111 joules per mole K, minus 1 times aluminum's entropy, plus 3/2 times chlorine's entropy. All right, all of that came from problem number 1, that table. All right, so what is our delta S using Big Mama? Let's get, now as far as sig figs go, we're adding and subtracting here, correct? Really, at the end of the day, that's what we're doing. So what do we round to? Least number of decimal places. So there's no decimal places in any of those, right? So you're just going to round to a whole number. And what is that whole number? Negative 251. I knew it was negative. That's why I hesitated. Joules per mole Kelvin. Let's make sure we can get that. We're going to be doing a lot of Big Mama calcs, so I want to make sure you know how to put that in your calculator. Are we good? Did it match our prediction? Yes, it did. We're awesome. Why is my phone blowing up? I'm not popular. That's the thing. It's Amazon telling me my package is arriving. And it has to tell me 3 times. Oh, yes, I didn't know that. It's negative 252 then? Okay. Someone said it was negative 251.5, so we need to change it to 252 joules per mole K. Thank you for the clarification. No, no, we're not playing the number line game. The thingy is just direction. So treat it normal. God, no one's ever asked me that question before. No, no, no. Oh my God, no. This magnitude you treat normal. This so at home, what the question was, since it's negative, should we really round it down to negative 251? No, no. No, but you're using the negative on the number line. No. The amount of entropy is 252. The negative tells us whether that's an increase or decrease in that amount. Oh my God, we're not talking about this. No, we just need to stop. That's horrible. Thanks for ruining my life, Matthew. Appreciate it. Okay, so now we're actually going to go through the process of finding out if this is going to be a spontaneous reaction based on finding the delta S of the universe. So we're going to take it through the process. This reaction was carried out at 100 degrees Celsius. We're making ammonia from elements. It says calculate the change in entropy of the system. I always want you to predict just to see, so you'll have a way to see if your number makes sense. So we're going from 4 moles of gas to 2 moles of gas. What do you think? Yeah, we should predict that the delta S is going to be negative because that's definitely less disordered. 4 moles of gas is way more crazy than 2 moles of gas. Okay, so we're going to predict that. So we're going to use the values that I have, I think on this, I've got them on both sides, to find our change in entropy. You're going to use Big Mama. So for those of you at home, this comes from a thermo table. We're going to take 2 times ammonia. Gas's entropy is 192.45. Oh my God, you've blown my brain. Now you're making me really think about it, and it's upsetting me. 1 times 192 plus 3 times 131. And the units on all of these is joules per mole Kelvin. So to know decimal places, because the 192 and the 131 don't have them, what would be our change in entropy of the system? System. Negative 200. How do I make that? Yeah, we're going to put a decimal here. Okay, negative 200 point joules per mole Kelvin. And it was negative as we predicted. Now the next step says calculate the change in entropy of the surroundings. How do we do that? Noah. Ooh. Negative delta H of the system. Yes, system divided by temperature. Just had to make sure we're still awake. All right, so how do I find delta H of the system? And then I'm going to plug it into that. So I'm going to do delta H of the system over here. What do? The system. Big Mama, using the ways I already know how. Anything of the system is the way you know how. So we know that the delta H of the product is negative 46.11. I'm looking at the board. minus, and those are all free elements, right? Delta H of free elements are 0. So what's 2 times negative 461? What? Times 2. Louder? I can't hear anybody. So negative 92.22. This is the units of kilojoules per mole. So now I take that negative 92 and plug it in here. So a negative and a negative makes this a positive. Oh, why did that do that? Positive 92.22 kilojoules per mole divided by, what's my temperature? Good, he didn't get trapped. It's 100 degrees Celsius, but entropy is always in Kelvin. What? We're going to do that, but we're not yet. Right now we're just trying to find this. We will have to multiply it by 1,000. So this is 373 Kelvin. So right now, what is my kilojoules per mole? 0.2472 kilojoules per mole Kelvin. So now we have our delta S of the surroundings right here. Delta S of the surroundings. We have our delta S of the system, which we just calculated. We're going to add them. And JD brought up the point that you're going to have to change one of them. You can't add kilojoules to joules. Biggest mistake students make in this unit. So I tend to go to joules. There's no rule that you have to, but the way these problems are layered, you might have a rat link problem or a negative NFE problem or something where you have to use the constant R, or you'll have to do something where it's got to be in joules in order for it to cancel, and it's always in joules when you have to do those problems. So I say convert it to joules. So we get negative 200 point joules per mole K plus 247.2 joules per mole K. I just multiplied the delta S of the surroundings by 1,000. Does everybody understand what I did there? I'm hoping you can do the joule, kilojoule transition without having to do stoichiometry at this point. Yes? You'd be surprised. All right. What is our delta S? 47. Oh, this? Oh, yeah. I just got dyslexic. I didn't even get dyslexic. I just didn't do it right. All right. So what's the answer? 47 joules per mole K. So this is my delta S of the universe. Is the reaction spontaneous, and why? Yes, because the delta S of the universe is positive. So please don't ever make the mistake of thinking you can look at delta H of the system or delta S of the system by itself to determine spontaneity. You can't. Okay, you always have to either do delta S of the universe or calculate delta G, which we will do tomorrow. All right, let's do a little more. Oh, no, we're not going to do a little more. I do want to talk about one other thing. And you guys seem to have a pretty good handle on looking at an equation and determining if it's spontaneous, or determining if the entropy is going up or down, looking at the states, right? You have no problem with that. Well, let me give you a scenario. This was a problem that I graded in the dungeon a few years back at the AP many years ago. But I was shocked about how many students got this concept wrong. Most of the nation got it wrong. And you have a hot plate. That is a hot plate. Might not look like it, but it is. And then you've got water in the beaker, okay? And you're going to put a piece of copper into boiling water. So that's what's going on. You got a piece of copper in there, started at room temperature, they put it into the beaker, and the water was boiling. So then they started asking questions about the copper. So they said, from beginning to end, what was the delta H of the copper? Was it negative, positive, or didn't change? That was the options. What happened? You're taking copper and you're putting it into boiling water. Positive. Why? It's endothermic because it is absorbing energy, right? Is everybody good with that? Students had no problem with this one. Their next problem was delta S. And they were like, well, is it positive, negative, or did not change? So what do you think you might say to that? Do not change wasn't the most common response, and it was incorrect. It does go up a little bit. Why is that? Exactly. When you heat them up, the molecules are moving a little bit more quickly. Metals do expand a little bit when you heat them. So molecules are a little more disordered. So whenever there's an increase in temperature, even though we didn't change phase, there is still a change, slight, albeit slight, in the disorder, okay? So I blamed myself and all the other teachers out there who never really talked about this. We never even brought it up because it just never came up. And all of a sudden this shows up and I'm like, oh man, we got to talk about entropy within phase as well. Super temperature dependent. Okay, that's it. I'm done.